All right, welcome to Next Gen Manufacturing. You know, when you look at the machines that really define our world today, I'm talking sleek aircraft, high-performance cars, those massive wind turbine blades, they all have this look, don't they? Almost like they were carved out of a single solid piece of material. But of course, they weren't. They're all assembled from these incredible advanced composite parts, which brings up a really interesting question.
Exactly. Where are all the bolts, the rivets, all the fasteners you'd expect to see holding everything together? Well, the secret is they've been replaced by something way more advanced, structural adhesives. Today, we're going to dive deep into the incredible science of how we bond the future together. And trust me, we've moved way, way beyond just glue.
Okay, so this slide just lays it all out. On the left, that's the old way of doing things. Every single bolt adds weight, and even worse, every hole you drill creates a stress point, a built-in weak spot where things can start to fail. But now, look at the right. Adhesive bonding is a total game changer. You get lighter assemblies, the stress is spread out perfectly across the entire surface, you don't have to worry about corrosion, and let's be honest, you get those beautiful, clean, aerodynamic surfaces we were talking about.
But let's be super clear about something. This is not about grabbing a tube of superglue off the shelf, not even close. Structural bonding is a seriously sophisticated engineering system. It's a whole process where every single step is planned, calculated, and controlled with just incredible precision.
And this is why it's a true engineering decision. The advantages, they're huge. You get amazing resistance to fatigue, and you can join totally different materials together, like carbon fiber to metal, which is incredible. But you've got to look at the trade-offs. You can't just unbolt it later. The parts themselves have to be designed specifically for bonding right from the start. And here's the big one. It demands absolutely meticulous surface preparation.
And this, right here, is probably the biggest takeaway of our whole explainer today. The success or failure of a component that might be worth millions of dollars, it doesn't actually come down to the strength of the adhesive. No, it all comes down to what happens to the surface before that adhesive is even in the room.
Just let that sink in for a second. A single fingerprint. The oils from your skin can leave behind a microscopic layer that completely prevents the adhesive from forming a true chemical bond with the material. We're talking about a level of precision where the chemistry of the surface is literally everything.
So how in the world do they get it so perfect? Well, it kind of boils down to this three-step dance. First, a super deep clean to get rid of any of those anti-stick agents they use to pop the part out of its mold. Second, a very careful abrasion. Think of it like using superfine high-tech sandpaper to give the surface more texture for the adhesive to grab onto. And third, and this is the really cool part, they use these advanced treatments that actually change the surface at a molecular level.
And check this out. This is one of the cleverest ways they ensure that perfectly clean surface. Manufacturers will build a sacrificial layer of fabric, what they call a tear ply, right into the surface of the part. It's kind of like the plastic film on a brand new phone screen. It just sits there protecting the surface. Then, right at the last second before bonding, they just peel it away, and what's left underneath is a perfectly preserved, untouched, and chemically pure surface that's ready to go. So smart. But, sometimes even that isn't enough. For some really high-performance plastics that are just notoriously difficult to get anything to stick to, engineers have to turn to some methods that sound like they're straight out of science fiction. We're talking about using fire and lightning.
Okay, so let's break these down. On the left, you've got Flammage. A robot arm will literally pass a specially controlled flame over the surface for just a fraction of a second. It doesn't burn the part, it just chemically alters the surface molecules, making them way more receptive to the adhesive. Then on the right, you have plasma treatment. The part goes into a vacuum chamber, they pump in a gas, and then they blast it with energy to create a plasma. This plasma bombards the surface, scrubbing it clean on an atomic level and basically supercharging its surface energy.
And the results you get from this, they are just staggering. Look at this chart. For a regular polyester composite with no treatment, the bond strength is about 3.6 megapascals. Okay, but after you hit it with an oxygen plasma treatment, it jumps to 11.3 megapascals. That is more than 3 times stronger. And get this, we haven't even changed the adhesive yet. This is all just from preparing the surface the right way.
Okay, so now that we have that absolutely perfect surface, we can finally talk about the adhesives themselves, because you still have to choose the right substance for the job. And believe me, engineers have a whole toolbox of these specialized structural adhesives to pick from.
For most of the really high-strength stuff, it usually comes down to these 3 main families. You've got epoxies, polyurethanes, and acrylics. It helps to think of them as specialists, right? Each one has its own distinct personality and a totally different set of skills.
And the big choice between them often boils down to this fundamental trade-off: strength versus flexibility. At one end of the spectrum, you've got your epoxies. They are incredibly strong and rigid, but not very flexible. At the complete other end, you have polyurethanes. They're much more flexible, great at absorbing vibrations, but they have less of that raw strength. And then, sitting right in that sweet spot in the middle, you have the acrylics, which give you a really fantastic balance of both.
So, what does this look like in the real world? Well, an epoxy is your go-to for something like an airplane wing, where you need absolute, uncompromising rigidity that won't deform over time. A polyurethane is perfect for, say, bonding a composite car body panel to a metal frame, because its flexibility can handle the two materials expanding and contracting at different rates. And the acrylics, they're the powerful all-rounders, great for jobs that need to be done fast and have to withstand high impacts.
So we've prepped the surface like crazy, and we've picked out the perfect adhesive. We're done, right? Ha! Not even close. The final, and maybe the most critical piece of this whole puzzle, is the physical design of the joint itself. A great bond isn't just applied, it's engineered right from the very start.
And this right here is the golden rule of designing with adhesives. Look at the design on the left. It creates what's called a peel force. All the stress is concentrated on that tiny little leading edge, and it lets the bond fail by basically unzipping itself. But now look at the design on the right. By overlapping the parts, the force is now in shear, which spreads the load out across that huge surface area. This design is exponentially stronger. It's not even a fair fight.
And engineers take this principle to just incredible lengths. With composites, since they're made of all these different layers, designers can create these things called scarf or stepped joints. They actually cut back each layer in this precise, tapered pattern, so the load gets transferred super gradually and smoothly from one part to the other. And when it's done right, the bond itself can be just as strong as the material it's holding together. It's truly remarkable.
So, let's bring this all home. What we've seen is that next-generation bonding isn't just some newfangled replacement for rivets. It's a completely different philosophy of how to build things. It's a total system where the surface chemistry, the adhesives properties, and the mechanical design of the joint all have to work together in perfect harmony.
And when engineers get that system right, the results are just mind-blowing. By combining the perfect surface prep with the right adhesive and the smartest joint design, they can create bonds that aren't just 2 or 3 times stronger, but in some cases more than 10 times stronger than a basic, poorly designed joint. That is the power of next-gen manufacturing.
This whole shift to bonding has unlocked designs and created technologies that were just flat out impossible before, making everything lighter, stronger, and way more efficient. It really makes you wonder, as we keep pushing the limits of material science, what other invisible, powerful connections will we engineer to build the world of tomorrow? Thanks for watching.